Inserters, the most commonly used item in every single Factorio base. Because they're so commonly used, when you get to the very, very end of the game and you're trying to squeeze out every single ounce of UPS that you possibly can, you start to look at the things that are the most commonly used. So today we're going to talk about inserters. How do you control them? How does the game control them? How does the game know in this particular weird loop that I have that there's items in this chest and that it can pick it up and not to turn and swing the other ones? How can we manipulate the game engine into controlling these inserters ourselves and getting around the game engine, and can we make any UPS optimizations for that? We're going to talk about traditional methods on how we control them. We're going to go into some potential new methods of doing that, and then we're going to finally end the video with some UPS tests. At the very end of the video as well, if you stick around, there's going to be some blueprints for all the different designs that you see in here, along with the test results that you can look at yourself and you can reproduce if you want to. So without further ado, let's get into the video. So we're going to start off today by talking about the first concept, so a concept called wake lists. We were mentioning a second ago, how does the game actually know when to turn on and off an inserter and insert something and pick something up? Well, it uses a concept, and we're going to go into the debug menu here. We're going to go and enable two things. We're going to show the active state, and we're also going to show the wake lists. I've already checked them off for convenience, so I'm going to press F5 to bring up the debug menu. And we're going to look at this. So you're seeing this little pulsing yellow marker here. That indicates a wakelist target. I'm going to delete this to showcase that. So whenever an item is going to be looked at as a wakelist item, what that is this is a target that this inserter is subscribed to. When this particular furnace happens to be low on ore, it will call and the game engine will say, hey, wake up inserter, go do something. So that's one thing. The little red indicator here, this little red circle, means that this thing is currently considered to be inactive. The moment I put this inserter over here on the right, you're going to see that flicker, that little red state. Well, at the very late game, there are some concepts to get around this, and what we're going to try to do is try to control the inserter so that it isn't flickering as much, this little yellow target turning on and off. And you're also noticing here that this is getting a lot more updates where it's constantly checking this furnace than it actually needs to. So by default, this works completely fine. And if you're not going to get into the late game of mega basing, then just do this. This is perfectly good and perfectly fine. One other thing that I'm going to note for all the rest of these sections, I have this little indicator here. It just says when this furnace is working and when it's not. It's pink when it's not working. And that's just so that we can show that effectively for each design when a furnace is on or off, just purely for demo purposes. So enable clocking, what is that? So this is a concept that has existed for a long time. I'm going to link a original video that was created 4 years ago. So this is not a net new concept. What is this? This means that we're going to create a clock. And what is a clock? Well, it's basically a circuit, this little green line here that's looped back on itself. And it basically just outputs a single item, so like just one for a tick. And the clock iterates up and down. What does that look like in practice? I'm going to pause the game here, and we can look at this clock here. This is right now at the 15th tick. If I move one forward, it's counting the ticks in the game engine. Game has 60 ticks per second, so a 60 ticks in this case is 1 second in terms of the time for the game. So every single time this is clicking and iterating, you're seeing that this is counting up until 26 ticks are active, and then it will reset. This is technically actually going to be slightly less than that, because if you're looking at this here, if we go to 26 here and you go forward in time, this is going to be one off. So this is technically 27 total ticks that this is active for, because it starts at 0. So it's 0 to 26. So that actually is 27 items total. So if we did this and we went 27 items into the future, you'll see we'll wind up at the same place. So deterministic. So that's a good way to kind of control things in terms of ticks of the game engine. So we're going to go ahead and resume things. So that is a clock. We have two clocks. We have two different timing variables for those clocks. Why do we have those timing variables? Well, before I get into that, let's go ahead and talk about what they're doing. All this is doing is it's basically going to read, hey, whenever this clock is less than 4, at that point, go ahead and output an iron ore here. I've chosen iron ore as the activation signal just to make this really clear when you have the alt mode enabled so you can see what they're controlling, but you can use any activation signal, doesn't matter. So what this controller is going to be doing is it's sending a signal over to the inserter, and it tells it explicitly when to activate and turn on and turn off. So now what you're noticing, because I still have the debug menu turned on, you're seeing no more this, it's not relying anymore on the wake list anymore. What it's relying on now is a pure on and off state that's controlled by this clock here. What's nice about this also when you're looking at this is that it is exactly timing wise, we have set both of these up to exactly insert the iron ore when it is needed, and it is also pulling out the iron plates exactly when it's needed. So, and also this inserter here is always grabbing exactly 16 items whenever it runs. So we're going to run one tick at a time just to demonstrate that. So when this picks up an item from the furnace, it is going to go here, it's going to swing. It's disabled for this time. It picks it up in 2 ticks, grabs all the items from it, swings, dumps it all, and then comes back. And we're controlling this so that there's always a buffer of at least 16 items based on the clock, so that when this grabs it, as you just saw there, it grabbed all 16 items as the 16 and can swing and finish its job. This traditionally is the way that we have controlled electric furnaces, or just any kind of assembly machine where we want to clock the inserters. And this has been proven in the past already that this is a solid and reliable way to constantly be running a furnace and being able to slow down the inserter time and ultimately save UPS. So the question that I'm going to be posing in this video is this still the best method in space age? Or can we utilize the fact that we can read the contents and the contents included in crafting, so we can read how much is inside the actual furnace, this could also be assembly machines for that matter, to control this instead? And is it more UPS performant? So just to touch on this, I'm also going to be testing a filtered version of this, so setting the filters instead. Is this better than enable clocking? And finally, we're going to go into the new method that I'm trying to propose. So in my Megabase video, I use this concept a lot. I made the assumption that, like clocking, the circuit network is actually free because it runs in a multi-threaded context. So your main game loop is running in a single-threaded context, where it's just basically processing sequentially all the items that are in the game and doing something with them, rendering them, grabbing an item, transferring them, changing the inventory, etc. All the circuits run multi-threaded, so that means you can use all the cores of your CPU. Almost every single gaming computer that you're going to create nowadays has multiple cores, so let's take advantage of that. So my assumption here was this is going to monitor, say, whenever the iron ore is less than 16, let's go and insert something into it. An alternative, and then also on the output, it's going to do the same thing whenever it's 16. So this is effectively running in the same way, where it's constantly grabbing items from the furnace, but it's no longer using clocking. So this is what I'm calling a thresholded scenario. This is really nice because it's dynamic. As opposed to clocking, it's always going to happen at a fixed interval. When this effectively fills up completely, the moment that you add this inserter back, it's going to dump it much faster than it's actually producing. So that is a one that we want to test. A second one, sitting around in the Factorio, Technical Factorio Discord, we've been discussing this as a separate concept. We're also going to test this as, hey, instead of doing it on every single furnace, let's go and just have a lead follower concept. So this concept was not created by me. Flame SLA wound up actually coming up with the concept. I tried a couple different other methods that ultimately didn't work, but this was a concept that he had created as well for us to try out. So the way that this works is it's the same way. It's monitoring in this decider combinator now what is inside this furnace. So the assumption here is that both of these electric furnaces are going to be the same in speed. So if I hover over this, we can see that this is currently producing 47.95 and consuming 31.97 per second. Same on both furnaces. So if I click on both of these, they have the same speed. So if they're both the same speed, in theory, what you can do is enable the same logic, but just govern it so that this inserter is inserting into this furnace on a clocked speed. So you're seeing, again, the same behavior here, where we're grabbing both of these items, and these furnaces are synchronized. They're constantly outputting items onto this belt. But the difference is now you're only having to have one circuit network connected to one entity and only subscribing to that. So potentially this could be a more performant method as well over the original concept, which I use in my mega base for pretty much all the designs. So we're going to test out now all 5 of these different concepts, and I'm going to showcase that in a second what that testing scenario looks like. Before we get into the tests, I just want to make a quick note. There are some conditions on when exactly, if you really want to get into clocking. It is a very painful thing because you have to, when I was starting and pausing in the actual game engine, I was actually testing, and I have tested this, on exactly the number of ticks that are required for an inserter to pull something off of a belt and actually insert it into, in this case, it's an infinity chest that just deletes all the items the moment it puts it in, but it could be an assembler, whatever. So what you'll notice here is this is set up on a clock here, and all the clocks are going to be this way. So this is the total ticks that you have enabled, and that's when the clock resets, like we talked about before. Counts up to 30, so it's technically 31, and that's just to have all these the same as the display purposes. This is kind of irrelevant, but this is 4 ticks that it's enabled for. So we're going to go ahead and zoom forward a little bit to the point where this thing is going to reset, and we're going to get to this condition, and all right, we're resetting here. So if I look at this controller here, it's going to say, hey, this is now active, and this is considered active right now. Also by it's not yet for this tick, but it will be the next one, because there's always 1 tick delay for when a controller actually sets something. So it's going to send a tick. This isn't considered active yet, but the filter is going to be applied in the second tick. So now that's active. So now what it's going to do is for the first swing, it's going to grab 4 items. Then the second tick, it's going to grab, now we're going to have 8. And then still on its way, even though we have at this point said we are disabled, it really just needs those 2 ticks to kickstart it. And then the animation, the game engine is going to take it the rest of the way. So then it's going to click again. And even though the filter is set to be disabled, it's going to go ahead and drop all 16 items and put them into this infinity chest. That is different. And I have paused this at this frame for a very good reason. What you're seeing here is this is reproducible if you have both lanes filled, but it starts to get into more nuances when you have it on the far side or the near side only. And you're seeing here now it starts to take 6 ticks, so we're not fully within a swing for it to happen. And then just including the animation time down here, it's actually more ticks than that. I just have included that just to talk about how many ticks it's fully going to take to finish inserting it. Not necessarily going all the way back, so we'll go a couple more forward, but for it to ultimately finish completely, so it takes a little bit longer. Same thing over here, where if you have a free-flowing belt, it's also different. So up here in this scenario where we talked about it, if it's not a free-flowing belt, and what I mean by that is where there's back pressure, you need less ticks. So in general, that's a good concept for us to talk about. Back pressure is important for us to consider with all these different designs. If it's free flowing like this, or there's still more demand downstream than you're supplying, that's a good way to think about it. You're going to need more time to pull things off the belt, so more time for the inserter to be active. So just even if you don't do anything that's in this video, just having back pressure is already a good thing for inserters. So oversupplying downstream on your mining, for example. So you can see then just here again, free flowing, it actually matters if it's completely saturated or not for how long it takes to take something off. But when it's has back pressure and it's not free flowing, it does not matter which side of the belt it's on at all. So there's also some slight nuances which Konaj got into a little bit. I'll link his YouTube channel along with his Twitch as well. He went and did some extreme testing on a whole bunch of different types. If you have an underground belt, or if you have a regular belt and pulling from a splitter, etc., and the timing variables matter. What I'm going to tell you, and this is just kind of a spoiler, none of this is going to matter for some of the results that we're going to talk about later, so I wouldn't get too bogged down into the details. If you want a separate analysis on how do you calculate these values, it's basically just simply the math is just you take the amount of items that you can output per swing, so that's 16, divided by the speed of your machine. So in our case over here, I'll just explain this real quick. So when we got into clocking, this has an input of 34.9. You take 34.9, you divide it, or 16 divided by 34.9 times 60, so 60 ticks per second, because that's the speed of the clock that it's going to be. And that'll give us a number that is close to like 26 and 27 and change but slightly over 27, but we round that down to 26. Like I said before, this is actually 27 total ticks, and that's when the clock is going to reset. So then that gets us close to the value -1, and then you basically say that it's going to be enabled for 4, and that number 4 comes from the examples I just showed as the minimum number of ticks it takes for that animation to kick off. If this is already blowing your mind and you're going and saying this is like way too complicated for me, like I promise you it's going to get simpler, and we'll get into that soon. So here we are now with the test scenario. So what I've set up here is this is the same steel smelter setup that I have for my purple science, for example. I've used this in this test example as it's a pretty good use case of showing multiple inserters having to insert from a belt, a inserter going from a building to building, and then finally a building dropping down onto a belt. So the first item that we have is a wake list only. That means we'll press F5. It's fully relying on those little yellow lines and basically the wake up targets and subscribing to those entities on when it's going to insert something or pull something out of it. So that's the first example. We already know this is going to be the worst performer because we proved that has been proven by other people in the past, but I'm still using this as a baseline benchmark for us to utilize this. All these designs, and there's 5 of them total, they are all going to be outputting at 240 items per second. That's what they're throttled to. And that's going to be the case. And effectively, in the end, the test scenario is going to be we're going to grab 128 of these, and we're going to put them all into a simulator, run it at 100x speed, and then we're going to see what the results are. So the second design that we have is enable clocked. So this is the same concept that we showed before. This is going to turn on and off the inserters based on these clocks. Again, the clocks were exactly optimized like we talked before to be exactly when they need to be outputting from the furnace. And this is set up so that there is one network for both sides. So this green wire goes all the way around here. And if we just hold this here so we can see this, the green wire goes all the way around and is triggering all the inserters to swing exactly at the same time. Same concept again here, but now we're just setting the filters instead of enabling and disabling them. So this is the filter clocked example. Next, we're going to go into threshold. This is again the same concept that I use everywhere in my Megabase. This is just again here monitoring when the basically the input for this steel furnace is low. We're going to grab something and put it in there. Same thing here for when we're low on iron ore, we're going to put that in. So it's subscribing each time to these entities, and we're controlling it down by the circuit network. So this is the same concept that we're going to be using in the next one, but that one is now going to be using that lead follower concept where we're only listening to the first one and controlling all of them downstream. What the lead should always be the first item, so the one that has nothing upstream from it. So there should be no inputs that are going to be running, because this is going to be always the one that is, in general, in every single build, always running constantly. So this is a good one to use as your clocking base to subscribe to. Again, the wires run all the way around and come in, but now the difference is that they just have one thing that we're monitoring. So those are the 5 scenarios that we have for steel, and we'll talk about the results in a second. The second one that I want to do, just to reproduce this, is using those exact same concepts, but a slight smaller set, just because I don't think that it's important to include the wake list here. And what we're going to do here is this is just the threshold scenario. Again, this is one of the common designs that I use a lot in the Megabase video, but just for making 240 items now instead of steel, this is making iron. So we're going to do the same thing here. This is now using the clocking. Again, exactly the amounts that you're going to need to output the items onto here. This is already throttled by nature because this is going to be making 278 items per second, which is way overkill for it. And also I wanted to use it because these also have different timings. So this one makes 47.95, this one makes 43. So if you don't have a perfect scenario where every single steel here furnace is making exactly the same speed per second, does this still help? So if you have a more dynamic setup, and does it get better or worse if you have clocking versus threshold? And then finally, we have a couple different designs. Mainly this is just because I was testing the difference in having more beacons around the electric furnaces. So this makes 157, or rather 314, so way overkill. But it's just minimizing the amount of time that the furnaces are running. And in this version here, this is making 278. So the better example for all of these is really we're going to compare these 3 for the testing results, but I just included this here because I'm just curious myself if this is a better design. So that being said, let's go ahead and get into an example of one of the test files, and then we're going to go into the actual benchmarking. So here we are in our benchmark world. What this world is it is a very simple file of just an editor config world. There is nothing else in it. The only thing that we have is there are going to be 128 of these stacks, like we mentioned previously. We can just look at that by looking at the little purple values. So there's 256 total, divided by 2 because it's an input and output, so there's 128 stacks. What those are making constantly right now is these are making effectively here 1.8 million steel per minute. I don't expect that you're going to need this amount of steel, especially in uncommon, but who knows? Maybe your mega base needs a lot of steel and you really like it. So I'm not going to say that you won't use this setup, but I don't think you will practically use it. So this is just the reason we're having so many of these is so that the overall UPS, when we go to 100x speed, this is going to be at a relatively capped value, so that when we get more of a variance between all the different entities running, we have more load on the system, so we can start to really see if there's a difference between all the different effectively the different designs. So I've replicated this same setup here for all the different designs that we have. I have a test file, so there's gonna be 5 for this, and then also for the the steel that we're making, but also the iron plates. So the iron plates, the only difference is that instead of, it wasn't quite enough load for me to make 128 of them, so I made 256 of them. Why am I choosing 128 and 256? It's a really nice tileable value because it's divisible by 4 and divisible by 8. So it just makes it easy to set up and to copy and paste it. So that's the only reason. So with that, we're going to go ahead and get into the benchmarks and the actual results here in a second. And I will show a little bit about the benchmark setup here in a second. So before you click away because you're seeing a whole bunch of code, let me just rest assure you that you don't need to understand any of this stuff. I'll link it again, a link to where you can find all of this. I have a GitHub repo where I've posted all this. All this is a PowerShell script. All it does in the end is it runs the actual Factorio game and executes a special command called a benchmark, where it doesn't open the actual UI, and it's going to load a map that I choose. So I've put all the different maps in this file here in this folder. So in this case, this is the iron smelters. So those are all those zip files, which are just the game save files that I have set up. And what it does then is it runs it for a number of ticks. I've specified that up here as 5,000, and I'm realizing I should probably zoom in a little bit so everyone can see this. But what this does here is this is going to say, hey, cool, I want to run 5 times each of the maps, and I want to then, when I am done with the benchmark, I'm going to take some of the outputted results that are inside it, and I'm going to save it and extract a couple variables. So whenever you run the actual benchmark, it outputs some values at the end, and this is just doing some fancy stuff to just basically grab the contents of the output that are just strings and make them into values that we shove into a CSV file. And that's what this CSV file here looks like. And then afterwards, we just are going to look at now the results. I've already run these, so we're going to go ahead and get right into the data. So we're going to talk about here the inserter clocking method, like the base that I had. And this is going to be looking at the steel furnace scenario. So this is again open on my GitHub repo. So if you want to read more of this, you can. I'm just going to model this and show this here so that we can talk through it as well. Do I want to install the recommended PowerShell extension from Microsoft for the PowerShell language? No, thank you. So what we have here is the testing scenario. We talked about is 240 steel per second. They're going to be fully beaconed, or at least as many as I could possibly cram into here. There's 16 legendary furnaces, 8 smelting iron, 8 smelting steel. There's 24 legendary stack inserters per module. So what this is doing, each test contains 128 copies like we talked about before, camera and player models in the exact same location. Each run is executed for 10,000 ticks at 100x speed. So the blueprints that are used are linked here. It's also on the GitHub repo. So if you for some reason like these particular blueprints that I use, you can copy them. It's going to include every single version. There's going to be a clear winner, which we're going to get into, but we'll go into that. So here's a preview of that design like we talked about. And this is an overview of each of those different methods. So enable clocked, filter clocked, thresholds, and what it is for subscribing, and finally the lead follower example. There's one more that I experimented with, which was called threshold guarded, which was that same concept that this is again that another member on Discord figured out, but or Flame SLA rather, more specifically. But the concept here, and it was kind of spawned from this idea that I had of this guarding concept that, hey, I want to guard when the inserter is actually receiving a signal. So instead of having it constantly connected to the network and seeing every single tick or multiple times per tick that the item is increasing or decreasing, what this would do is it just adds now a decider combinator in between and only filters it when the value is low or high in this scenario. This ultimately was one of the worst performers, so I've scrapped it. Turns out you add more decider combinators. I'm not even including it in the results here. So here's the overview of the metrics for when we're talking about things. Higher UPS, better. The average frame time, the lower is better. So any of the frame time values, the lower it is, the better it is. So here are the results. The lead follower concept turns out to be the best that exists right now. So if you do any of these clocking methods, you're already going to get better UPS. If you do the threshold version that I had in my Megabase video, or the way that I originally did it, it already is a nominal improvement over it. It's not as good as the actual clocking that has existed, but what's nice to see here is that the lead follower example is way easier to set up because you just need a single decider combinator that is connected to the very first furnace or assembly machine, and you just have to specify in here very simply when you want the inserter to swing. So this is dynamic. From like a traditional controls theory concept, using time-based controls is just objectively worse than using a dynamic control system, like using these decider combinators to actually read the feedback meaning the amount of items that are coming from the target that you want to set something into, and then a target set point. So this is dynamic in that sense because, like I showed before, with the inserter swinging the moment that this furnace had over 16 items in it, it will continue to swing and actually would cause both of the inserters to continue to try to swing once this furnace is higher than that value, so if it's overclocked. So that is a huge benefit already to this because it simplifies drastically the entire concept of doing all the math to figure out the exact timing ratios of turning on and off inserters by a clock. This is still useful, however. Enable clocking is still the second best, and it's by a little bit that the lead follower example gets a little bit better than it. But it's still really useful for things where you can't actually read the contents of the furnace assembly machine, or more specifically for labs. We can't today read the contents of biolabs. So this is still the best scenario, is using a clock and controlling explicitly when the inserters are going to swing and put some items into the lab itself. So just to show a little bit of the percent differences. So compared to, and we've omitted the baseline wake list only, just using threshold already gives you 7% improvement in general. If you go into the filter clock scenario, so that's the same as the clocking scenario, but we're setting the filters, that's a little bit better, so 7.86%. And then if you do just the enable clocking, so not setting the filters on the inserters, then that is the first jump. That gets you to 11% of an improvement. So, you're looking at 7 to 11 here, so a 4% total improvement there compared to this one. And then finally, you can take it one step further and squeeze it out by just having the lead follower example, where you have a lead furnace and all the inserters downstream. Lead, again, just important. It needs to be the first furnace or assembly line that is going to be running constantly, because eventually you're going to want to saturate that line. So the last item is going to be usually a cap, unless it's exactly making 120 items per second to fill half a belt. Then it's most likely going to be more than that, because you're going to want to oversaturate it, so that you have, most of the time that's going to be the case that you're going to do. So you don't want to do it at the end, because the end is going to most of the time be idle. So you usually want to do it on the first one. That would be my recommendation. You can still test that out if someone wants to iterate on this concept and put it on the end and see if that makes a difference. but that would be my assumptions. You always want to do it on the one that's choked for resources and is constantly running. So, yep, that's the conclusion at the end. So I'm going to link a copy of the blueprints for this and the best ones that came out of it, and so that people can use it and use it for their other designs. So quickly, I'm going to touch as well on the iron smelter. So same concept there. Let's go ahead and open the preview, and we can open this. This is a really good format. If you've never used Markdown, love it. It's super simple because you just literally can just type things normally in it, like without having to worry about styling, and then you just let something else render it, which is a wonderful thing. So in this example here, same exact concept that we showed before with the different types of iron smelters, and I've demoed each one just so that we can see them. Similar setup. I ran it at 1000x speed, and the benchmark is 5000 ticks and 5 samples that are run per save file. And the results are exactly the same, where we're seeing that there is a, although here it's a little bit tighter, but here it was interesting just to see that the enable clock was actually objectively worse in this particular scenario than the lead follower followed, and in this case the threshold was slightly better. My assumption here is because of the mix of different speeds that the inserters are active more than they actually need to, so it made it so it's unbalanced. And so this is also showing that this lead follower concept is actually better too for mixed designs where you don't have the same speed on all of the different furnaces. Again, just making sure that the one that's downstream is the lead and all the rest of them are just going to follow from there. So although it's not a huge improvement, the second design that I showed of the mini having slightly less beacons around the furnaces versus a fixed speed on all the furnaces and having as many beacons that could be around the furnace that is, so it was just maximized. That was slightly better, and that also just makes sense intuitively because the furnaces are going to be running less. It's overclocked to run faster than the actual belt will actually allow items to go through. So that was a slightly better design. No, but not by much. So it doesn't, but if you really care, and like again, this whole video, the whole concept is let's squeeze as much UPS out as you can. This would be the better version to use, but if for some reason you're really space compact, this lead follower mini version that I have, again, blueprints are going to be included. That is going to be still good enough for most cases. If you've made it this far in the video, thank you so much for watching. This was an extreme technical deep dive into inserters and how to control them and squeeze as much UPS as you possibly can out of it. This went over some traditional concepts such as enable clocking, which has the downside of, again, being really hard to control and, well, not control, but to actually calculate the values that you wind up needing for it. And I'm really pleased as well that the concepts that I used in my Megabase video were not too far off, but definitely weren't the most optimal solution. So the lead follower example that we have here on the right, again, special shout out to Flame SLA for figuring out this idea and this concept here and iterating on my pretty terrible guarded concept and just making it objectively better. So this is so much simpler to set up, and I'm really happy that this is a concept that we can use now in Space Age to make clocking a much easier thing now for megabasing. I'm going to be incorporating the lead follower example in my future designs as I go back through my science build and optimize them. So stick around if you want to see those. This video is a point of reference so that I do not have to go back and explain this concept every single time I go through one of those science builds. So that is what I'm going to be referencing for future videos. So I just wanted to create this as a short video to quickly explain this concept and some of the testing that was involved. Again, all the links of everything that I've talked about will be in the video description below. One last thing, just special shout out to all the people in the technical Factorio group for their help and contributions to this. They were very good at explaining all the things that I did wrong, as this is the first time I'm getting into benchmarking and actually using the benchmarking tools that are available within Factorio. So if you want to see more of a deep dive into that on how you do that yourself, I could create a tutorial on that in the future, but there's also really great documents that already exist out there that can explain that as well. So thank you so much for watching. My name is Abuck Nasty. Have a fantastic day.